there are more objects orbiting the Sun beyond Neptune right now than there are stars you can see from Earth with your bare eyes. We visited exactly one of them up close, one out of hundreds of thousands of known objects, and those are just the ones we've found so far. In August 1992, two astronomers at the University of Hawaii stared at a computer screen comparing images of the same patch of sky taken several days apart. They were looking for something that moved. Their colleagues thought it was probably a waste of time. Then a single dot shifted position. That dot, now catalogued as 1992 QB1, about 160 kilometers across and sitting roughly 6.2 billion kilometers from the Sun, was the first confirmed object in what we now call the Kuiper belt. That discovery was 33 years ago. Since then, we've found thousands more. We've sent one spacecraft through the region. It took 9.5 years to get there. We've watched that spacecraft image a frozen, double-lobed object 6.6 billion kilometers from Earth, and had to wait 6 hours for the signal to reach us, even traveling at the speed of light. And still, after 3 decades of study, the Kuiper belt is holding back its most important secrets. We think something large might be hiding out there. Something we haven't seen. A planet, possibly, orbiting the Sun at distances so extreme it would take thousands of years to complete one lap. Something whose gravity is quietly tugging on distant objects in ways the math can't otherwise explain. We don't know if it's real. We don't know where it is. We're not even certain it exists. But the numbers keep pointing to it. This is the story of the edge of the solar system, what we've found, what we've missed, and what might still be out there, waiting. Chapter 1. The border that isn't where you think most people, if you ask them to picture the solar system, imagine the Sun at the center, 8 planets in a flat disk around it, and then nothing. Space. The endless void starts where the planets end. That picture is wrong, not slightly, fundamentally. The 8 planets all orbit within about 30 astronomical units of the Sun. 1 astronomical unit is the average distance from Earth to the Sun. About 150 million kilometers. Neptune, the farthest planet, sits at roughly 30 astronomical units, or 4.5 billion kilometers from the Sun. That sounds like a lot. It isn't, because the solar system doesn't end at Neptune. If it ends anywhere, it ends somewhere between 50,000 and 100,000 astronomical units from the Sun. That's the estimated outer boundary of the Oort cloud, the vast spherical shell of icy objects that surrounds everything. The Kuiper belt sits between 30 and 50 astronomical units. It's technically right next door in solar system terms. But right next door here still means an object in the outer Kuiper belt is nearly 7.5 billion kilometers from the Sun. Light traveling at 300,000 kilometers per second takes more than 6 hours to get there. The belt itself is shaped like a wide, flattened torus. Imagine a donut stretched horizontally and wrapped around the entire solar system. It's roughly 20 astronomical units across. It's also slightly tilted relative to the flat plane where the planets orbit, with most of its objects staying within about 20 degrees of that plane. Inside this ring, astronomers divide objects into three broad populations. The first group is called the cold, classical Kuiper belt objects. Cold here doesn't refer to temperature. The entire belt sits at around -220 degrees Celsius, which qualifies as cold by any reasonable standard. It refers to orbital behavior. Cold, classical KBOs have nearly circular orbits, relatively low inclinations, and sit mostly between 42 and 47 astronomical units. These are thought to be the most undisturbed, oldest residents of the outer solar system. They've been sitting in roughly the same orbits for over 4 billion years. The second group is the resonant KBOs. These are objects locked in precise mathematical orbital ratios with Neptune. For every 3 orbits Neptune completes, a resonant KBO completes exactly 2. Or for every 2 Neptune orbits, the KBO completes 1. Pluto belongs to this group. It's locked in a 3-to-2 resonance with Neptune, completing 2 orbits for every 3 Neptune makes. This resonance is so common that objects sharing it have their own name: Plutinos. The third group, the scattered disk, is where things start getting strange. These are objects that were gravitationally ejected from the main belt by close encounters with Neptune billions of years ago. They follow highly elongated, eccentric orbits that can carry them out to 100 astronomical units or more from the Sun before swinging them back inward. We'll come back to the scattered disk. Several of the biggest open questions in planetary science live there. The total mass of the Kuiper belt today is estimated at between 1/100th and 1/10th of Earth's mass. That's small. For comparison, the asteroid belt between Mars and Jupiter contains less than 4% of the Moon's mass, so the Kuiper belt is significantly larger in both mass and total count. But early solar system models suggest the outer region once contained somewhere between 30 and 100 Earth masses of material. Something removed almost all of it. That something is one of the most consequential events in solar system history. Chapter 2. The Man Who Didn't Actually Predict It. The Kuiper belt is named after Gerard Kuiper. This is, historically speaking, a little awkward. Because Gerard Kuiper, a Dutch-American astronomer working at the University of Chicago in 1951, actually argued that no such belt should currently exist. Kuiper published a paper that year suggesting a disk of icy bodies might have existed in the early outer solar system. The reasoning involved short-period comets with orbital periods under 200 years, like Halley's Comet. These comets had to come from somewhere nearby, because long orbits from distant regions would produce long-period comets, not short ones. Kuiper proposed that a residual disk beyond Neptune might supply them. But then he concluded that Pluto, which astronomers at the time thought was much more massive than it actually is, would have gravitationally scattered those objects away billions of years ago. So, while a disk might once have existed, Kuiper believed it was essentially gone by the time he was writing. He was right about the idea, wrong about the outcome. The disk survived because Pluto isn't massive enough to clear it. We didn't know Pluto's true mass until 1978, when astronomer James Christie at the US Naval Observatory discovered Pluto's largest moon, Charon. That discovery made it possible to calculate Pluto's actual mass from orbital mechanics. The answer was startling. Some pre-Charon estimates had placed Pluto at several Earth masses. The actual number is 0.002 Earth masses, smaller than Earth's moon. With a mass that small, Pluto has essentially no gravitational influence over the surrounding belt. The belt that Kuiper said shouldn't exist had been sitting there the whole time. His name got attached to it anyway. The person with a more accurate modern prediction was actually Kenneth Edgeworth, a retired Irish military officer turned astronomer, who proposed in papers from 1943 and 1951 that the outer solar system beyond Neptune likely harbored a large population of small, icy objects, and that short-period comets were probably members of this population that had been perturbed inward. Edgeworth's reasoning was sound, and many astronomers, particularly outside the United States, now use the name Edgeworth-Kuiper belt. But when the first confirmed trans-Neptunian object was found in 1992, Kuiper's name had more currency in the field. The discoverers were David Jewett, then a professor at the University of Hawaii, and Jane Liu, his graduate student. They began the search in 1987. The instrument was the 2.24-meter telescope on Mauna Kea. The method was painfully slow. Photograph the same patch of sky twice, days apart, compare the images pixel by pixel, look for anything that moved. For 5 years, they found nothing. The search wasn't widely respected. Trans-Neptunian space was assumed by most planetary scientists to be largely empty. There wasn't strong institutional support for spending years looking for objects that probably weren't there. Jewett and Liu kept at it. On August 30th, 1992, QB1 appeared, a faint dot that moved, about 160 to 200 kilometers across, orbiting at 44 astronomical units with a slight 2.2-degree tilt, taking roughly 289 years per orbit. Within 3 years, they had found a dozen more objects. By 2000, the count was above 400. Today, it's in the thousands, and those are only the objects large enough and bright enough for current technology to detect. Chapter 3. What's actually out there? The Kuiper belt is not a dense field of rocks and ice colliding constantly. It's mostly empty. If you were flying a spacecraft through the heart of it, which New Horizons actually did, you'd almost certainly see nothing interesting out the window. The objects are real, but the distances between them are enormous. Here's a useful comparison. The asteroid belt between Mars and Jupiter sounds dangerous. In movies, ships are always dodging asteroids. But if you picked a random point inside the actual asteroid belt, the nearest sizable object would probably be more than 1 million kilometers away. The Kuiper belt is even more sparsely populated. The objects that are there are made primarily of ice. Not just water ice, frozen ammonia, frozen methane, frozen carbon monoxide, and various combinations of these. Different ices have different melting points, different densities, and different spectral signatures, which means astronomers can identify what's present from billions of kilometers away, just by measuring which wavelengths of light an object reflects and absorbs. Surface color tells part of the story. A typical Kuiper belt object appears red, not vivid red, but a dull, dark reddish-brown. This color comes from tholins. Tholins are complex organic molecules that form when simple ices like methane and nitrogen are hit with radiation over very long periods. The outer solar system is constantly bathed in cosmic rays and solar ultraviolet radiation. Over 4 billion years, that radiation cooks the surface ice into a complex, sticky chemical soup. Tholins are why Pluto's surface is partly reddish-orange, why Arakoth is the colour of a rusted pipe, and why many other KBOs look similar. These tholins are scientifically interesting for a specific reason. They're old, in some cases essentially unchanged since the early solar system. They're a chemical record of conditions in the protoplanetary disk before the planets finish forming. You can't find that record on Earth. Earth's surface has been recycled by plate tectonics, volcanism, erosion and biology for billions of years. A frozen KBO, sitting quietly at 44 astronomical units, hasn't been significantly altered. Size-wise, known KBOs range from about 1 kilometre across, roughly the minimum our telescopes can currently detect at those distances, up to 2,377 kilometres for Pluto. Between those extremes, there's a population of larger objects that qualify as dwarf planets. Eris, at about 2,326 kilometres, Makemake at roughly 1,430 kilometres, Haumea at around 1,960 by 1,500 by 1,000 kilometres. Haumea is notably elongated, more egg-shaped than spherical due to its rapid rotation, and Quaoar, confirmed as a dwarf planet in 2023, sitting at about 1,100 kilometres across. One of the more surprising early findings from KBO cataloguing was the binary fraction. Roughly 30% of cold classical KBOs appear to orbit in pairs, two objects circling a common centre of gravity. This is dramatically higher than in the asteroid belt, where binaries are much rarer. The reason matters. High-speed collisions break binary pairs apart. If these objects regularly collided at high speeds, you wouldn't see 30% binaries. The high binary fraction suggests these objects formed slowly and gently in a relatively calm environment, probably by the gradual gravitational collapse of loose clouds of smaller particles. This gave early support to a formation model called streaming instability, where turbulence in the protoplanetary disk creates dense clumps of solid particles that collapse under their own gravity before anything violent can break them apart. The best available evidence for this model arrived in January 2019, when New Horizons flew past a small KBO called Arakoth. Chapter 4. Pluto. Before going further out, the script needs to stop here, because Pluto is the Kuiper belt's most famous object, and its story is inseparable from how long it took the scientific community to understand what the Kuiper belt actually was. Clyde Tombaugh discovered Pluto on February 18, 1930, at the Lowell Observatory in Flagstaff, Arizona. He was 24 years old. He found it using a blink comparator. a device that rapidly alternates between two photographic plates of the same sky region, so that any object that moved between exposures appears to flicker. He had been systematically scanning the sky for months. For 76 years after that discovery, Pluto was the 9th planet. Then, in 2005, astronomer Mike Brown and his team at Caltech discovered Eris. When its size was first estimated, it appeared to be larger than Pluto. Later, more precise measurements, made possible by watching Eris's moon Dysnomia and by observing a stellar occultation in 2010, showed Eris to be about 2,326 kilometers across, very slightly smaller than Pluto's 2,377 kilometers. But Eris is denser than Pluto and significantly more massive by about 27%. This created a classification problem. If Pluto was a planet, then Eris almost certainly should be too. And if Eris qualified, then the catalogue of large trans-Neptunian objects that Brown and others were building suggested there could be dozens of similarly sized bodies out there. The planet count would need to expand, potentially significantly. The International Astronomical Union held a vote in Prague in August 2006 to resolve this. The result was the current definition of a planet. It must orbit the Sun, it must have enough mass for self-gravity to pull it into a roughly spherical shape, and it must have gravitationally cleared the region around its orbit. That third requirement is the decisive one for Pluto. Pluto hasn't cleared its orbit. It shares the 3:2 resonance zone with hundreds of other Plutinos. Neptune's gravity actively moves objects in and out of that resonance. Pluto itself is gravitationally dominated by Neptune. Under the new definition, it became a dwarf planet. Mike Brown, whose discovery of Eris triggered the reclassification, wrote a memoir about the episode titled How I Killed Pluto and Why It Had It Coming. The public reaction was considerable. Some people felt genuinely angry. The word Plutoed briefly entered dictionaries as a verb meaning to demote. Astronomy received more mainstream attention over Pluto's reclassification than over almost any scientific event in the preceding decade. Scientifically, the reclassification is defensible. Pluto is more similar to a large KBO than to any of the 8 recognized planets. Its surface chemistry, its orbital characteristics, its size, all of it fits the Kuiper belt context. Calling it a planet alongside Jupiter or Earth created a category that was doing more harm than good to people's mental model of the solar system. But Pluto didn't change. The rules changed. And in 2015, when a spacecraft finally arrived after 9.5 years of travel, the world was reminded that labels don't affect what's actually there. Chapter 5. New Horizons. New Horizons launched on January 19, 2006, the same year Pluto was reclassified. The timing was coincidental, but fitting. At launch, it was the fastest spacecraft humanity had ever sent into space, moving at about 58,000 kilometers per hour. Even at that speed, it took 9.5 years to reach Pluto. The spacecraft went to sleep for most of the journey to conserve power, waking periodically for system checks. On July 14, 2015, New Horizons made its closest approach, 12,500 kilometers above Pluto's surface. The encounter lasted about 30 minutes of genuine close-approach science. After that, the geometry had changed and the spacecraft was moving away. The images took about 16 months to fully download to Earth, given the data rate at that distance. What those images showed rewrote the assumptions about the outer solar system completely. Scientists had expected a geologically dead world, a heavily cratered, inert ball of frozen rock, essentially unchanged since the early solar system, like a large dark version of some of the smaller moons in the outer solar system. They got mountains. Mountains of water ice jutting 3,500 meters above the surrounding plains. These are comparable in height to the Rockies, and they're geologically young, probably less than 100 million years old. In a solar system that's 4.6 billion years old, 100 million years is recent. Something is still actively building these features. They found Tombor Regio, named for Pluto's discoverer, a pale, heart-shaped region roughly 1,600 kilometers across. Its western lobe, called Sputnik Planitia, is a flat expanse of nitrogen ice almost entirely free of impact craters. This matters because craters are how astronomers estimate age. More craters means older, less cratered means younger. Sputnik Planitia has almost none. It's being constantly resurfaced. The resurfacing mechanism is convection. The nitrogen ice is slowly churning in cells roughly 30 to 40 kilometers across, driven by heat from below. The warmer ice at the bottom rises, cools at the surface, and sinks again. The same basic process as a lava lamp, or the convection in Earth's mantle, but made of frozen nitrogen and moving much more slowly. There's also evidence of glaciation. Nitrogen ice appears to flow down from surrounding highlands into Sputnik Planitia, forming what look like glacial lobes, slow rivers of solid ice creeping under gravity. Some models now suggest Pluto may have a subsurface liquid water ocean, kept from freezing by radioactive decay in its rocky core and by pressure from the overlying ice. This remains genuinely uncertain. The evidence is indirect, primarily from modeling Sputnik Planitia's gravitational signature and from the lack of expected surface deformation. It has not been confirmed observationally, and this is the honest version. We don't fully understand what's powering Pluto's geology. The accepted thermal models struggle with the heat budget. A body this small, this far from the Sun, receiving so little solar energy, should not have enough internal heat to sustain active ice convection, young mountain ranges, and possible liquid water. Either our models of small-body geophysics are missing something important, or there's a heat source we haven't correctly accounted for. Possibly both. After its Pluto encounter, New Horizons continued outward into the Kuiper belt, targeted at a second object. That object's name is Arrokoth. Arrokoth was discovered in 2014 using the Hubble Space Telescope specifically to find a suitable target for the extended New Horizons mission. It was an extremely demanding search. The spacecraft's trajectory after Pluto covered only a narrow corridor of sky, and the target had to be both reachable and scientifically interesting. New Horizons reached Arakoth on January 1st, 2019. The spacecraft was 6.64 billion kilometers from Earth. A radio signal traveling at the speed of light took 6 hours and 8 minutes to make a one-way trip. Arakoth is a contact binary. 2 lobes, the larger one Wenu, about 20 kilometers across, and the smaller one, Weo, about 15 kilometers, are gently pressed together at a narrow neck. The shape is sometimes described as a snowman, but the shape is not the important part. The important part is what the shape tells us. The 2 lobes have nearly identical colors and compositions. Their surfaces look the same. If they'd collided from different regions of the solar system at any significant speed, you'd expect to see differences from the mixing and heating of impact. You'd also expect cratering, deformation, and structural damage at the contact point. Instead, the neck is clean. The lobes match. They were clearly orbiting each other for a long time before they slowly spiraled together and made contact. The orbital decay was caused by radiation pressure, specifically by a process called Yorp-Torque, where asymmetric emission of thermal radiation from a rotating object gradually changes its spin and orbit. This confirmed that violent high-speed collisions are not the dominant formation mechanism for cold classical KBOs. The evidence points strongly to streaming instability, the gentle gravitational collapse of a local cloud of particles into 2 bodies that then slowly coalesced. Chapter 6. The Violent Past. The Kuiper belt you see today is a remnant. Current estimates put the total mass of all Kuiper belt objects at somewhere between 0.01 and 0.1 Earth masses. Solar system formation models, the ones that successfully reproduce the orbital structure of the giant planets, require the early outer solar system beyond Neptune to have contained somewhere between 15 and 50 Earth masses of material. That gap is enormous. Most of it is gone. The question is where? The leading answer involves a proposal called the NICE model, published in 2005 by a team including Rodney Gomez, Hal Levison, Alessandro Morbidelli, and Cleomenis Tsiganis. It was named after the city in southern France where the researchers were working at the time. The NICE model proposed that the giant planets, Jupiter, Saturn, Uranus and Neptune, formed in completely different orbits than where they sit today. In this picture, Jupiter started at roughly 5.4 astronomical units. Saturn sat at about 8.7 astronomical units. Uranus and Neptune were much closer to each other, and both were closer to the Sun than Neptune is now. Beyond them sat a massive disk of icy planetesimals extending from about 15 astronomical units outward, the original material from which Uranus and Neptune themselves had grown. For several 100 million years, this configuration stayed relatively stable. The disk and the planets maintained an uneasy equilibrium. Then Jupiter and Saturn drifted into a 2-to-1 orbital resonance, Saturn completing exactly 1 orbit for every 2 Jupiter orbits. This particular resonance pumps energy into a system instead of damping it. The gravitational interactions between Jupiter and Saturn amplified dramatically. Their orbital eccentricities grew. This destabilized the orbits of Uranus and Neptune, throwing both planets outward on elongated paths. Neptune, in particular, migrated from roughly 18 astronomical units to its current 30 astronomical units. As it moved outward, it crossed through the dense primordial disk. The interaction was catastrophic for most of the disk's contents. Objects in the disk were flung in all directions. The majority were scattered into the inner solar system or ejected entirely onto hyperbolic trajectories, meaning they left the solar system altogether. The fraction that survived in stable orbits became the Kuiper belt. The fraction thrown inward became a prolonged bombardment of the inner planets. This event is now called the Late Heavy Bombardment, and it appears in the crater record of the Moon, Mercury and Mars as a period of intense impact between about 4.1 and 3.8 billion years ago. The bombardment may have been responsible for delivering substantial amounts of water and organic material to the early Earth, or it may have repeatedly disrupted any early life that had begun forming. Possibly both happened at different points. The NICE model explains several things simultaneously: the orbital positions of the outer planets, the structure of the Kuiper belt, the late heavy bombardment, and the overall depletion of the outer disk. These are not trivial things to explain. The model earns its prominence. But, and this is important, the NICE model has also been significantly revised since 2005. Some versions of it produce outcomes that don't quite match the precise orbital architecture we observe. There are updated variants, including what researchers call the jumping Jupiter scenario, where Jupiter makes a rapid discontinuous jump in orbital position rather than drifting smoothly, that better reproduce the details. The general idea that the outer solar system went through a period of massive dynamical upheaval seems well supported. The specific mechanism is still being refined. Chapter 7. Where the belt gets weird. At around 48 astronomical units from the Sun, something unexpected happens. The density of Kuiper belt objects doesn't gradually fade out the way a diffuse disk of debris normally would. It stops abruptly. The number of detectable KBOs drops sharply at roughly 48 astronomical units in a feature now called the Kuiper cliff. This was unexpected. Neptune's gravitational influence, specifically the ability of Neptune to scatter objects from their orbits, doesn't fully explain a cutoff at 48 astronomical units. Neptune's strongest resonances extend to about 50 astronomical units, which helps somewhat, but the sharpness of the drop is steeper than Neptune's influence alone can produce. Several explanations have been proposed. One is that an undiscovered planetary body passed through the outer Kuiper belt at some point in the past, clearing out that region gravitationally. Another is that the primordial disk of material simply didn't extend much beyond 50 astronomical units, that the disk had a natural outer edge close to where the Kuiper cliff is. A third possibility involves the solar system's early stellar neighborhood. The Sun formed in a cluster of thousands of stars, and in the first few 100 million years, passing stars could have been much closer than any star is today. A close stellar encounter could have stripped material from the outer disk, creating a real outer boundary at roughly 48 astronomical units. We don't know which of these, if any, is correct. Beyond the main Kuiper belt lies the scattered disk, a population of objects with highly elongated orbits, mostly the result of gravitational kicks from Neptune during the period of planetary migration. These objects can swing within 30 astronomical units of the Sun at their closest, and then climb out beyond 100 astronomical units at their farthest. The scattered disk is where some of the solar system's most puzzling objects live. Sedna was discovered on November 14, 2003, by Mike Brown, Chad Trujillo, and David Rabinowitz using the Samuel Oschin telescope at Palomar Observatory in California. It sits between roughly 76 astronomical units at its closest approach to the Sun and somewhere around 940 astronomical units at its farthest. One orbit takes approximately 11,400 years. Sedna is estimated to be between 995 and 1,060 kilometers across, solidly in dwarf planet territory by size, though the IAU has not yet formally classified it as one. Its surface is one of the reddest in the solar system, suggesting a thick layer of ancient tholins. None of that is what makes Sedna extraordinary. What makes Sedna extraordinary is that 76 astronomical units is its closest approach to the Sun. Neptune is at 30 astronomical units. There is a 46 astronomical unit gap between Sedna's nearest point and Neptune's orbit. Neptune cannot be responsible for Sedna's orbit. The gravitational interaction simply doesn't reach far enough. Something put Sedna there, and we don't know what. In 2012, a second Sedna-like object was discovered. 2012 VP 113, informally nicknamed Biden because the VP in its designation stands for Vice President. Its perihelion is 80 astronomical units. Same problem. Neptune can't explain it. As of 2024, there are roughly 15 to 20 known objects with perihelia beyond 50 astronomical units. Their orbits aren't randomly oriented in space, they cluster. Their ellipses point in roughly the same direction. Their orbital planes tilt similarly. The odds of this being random chance are low. How low depends on exactly which objects you include in the analysis and how you account for observational bias, which is where the scientific debate gets heated. But this orbital clustering is what drove two astronomers to propose something striking. Chapter 8, Planet 9. In January 2016, Konstantin Batygin and Mike Brown published a paper in the Astronomical Journal titled Evidence for a Distant Giant Planet in the Solar System. They had analyzed the orbits of 6 extreme trans-Neptunian objects, bodies with perihelia beyond 30 astronomical units, and aphelia in the several hundred astronomical unit range. All 6 had something in common. Their orbits were physically clustered, aligned in the same direction in space, as if something was herding them. The probability of 6 randomly orbiting objects having this alignment by chance, they calculated, was about 0.007%, 1 in around 15,000. Their proposed explanation, a single planet with a mass of 5 to 10 Earth masses, following a highly elongated orbit with a semi-major axis of roughly 400 to 800 astronomical units. At its farthest point, this planet would be 1,000 to 1,500 astronomical units from the Sun. At its nearest, it might come within 200 to 300 astronomical units, still far enough to have completely evaded detection so far, since even a Neptune-sized body becomes extremely faint at those distances. This hypothetical body became known as Planet 9. The hypothesis attracted immediate attention, partly because of its boldness and partly because Batygin and Brown were making specific, testable predictions. They predicted the approximate region of the sky where Planet 9 should currently be, which orbits it should perturb, and what kind of telescope observations could confirm or deny it. Since 2016, the evidence has become more complicated. Several additional extreme KBOs discovered after the original paper appeared to support the clustering. Others didn't fit as cleanly. In 2021, Kevin Napier at the University of Michigan and colleagues published a reanalysis arguing the clustering is a selection artifact, that telescopes conducting surveys of the outer solar system tend to concentrate on specific patches of sky, meaning objects found in surveys appear clustered simply because the surveys were pointed at the same places. The clustering in this interpretation reflects where astronomers were looking, not where a planet was pushing objects. Batygin and Brown have countered this analysis, arguing that even after accounting for survey selection effects, a statistically significant cluster remains. The argument continues in the literature. What makes Planet 9 compelling, beyond just the orbit clustering, is that it would independently explain several other observations that don't obviously connect to each other. It would explain Sedna's orbit, specifically why Sedna's perihelion is so far from Neptune. A massive distant planet could have driven Sedna's perihelion outward over billions of years. It would explain why some extreme KBOs have orbits tilted nearly 90 degrees relative to the ecliptic, roughly perpendicular to the flat plane of the solar system. The modelling shows that a distant massive planet in an inclined orbit can produce this population of highly tilted objects through secular gravitational interactions over billions of years, and it might explain a known but oddly persistent puzzle. The Sun's rotational axis is tilted about 6 degrees relative to the average orbital plane of the 8 planets. This is called the solar obliquity. There's no completely satisfying explanation for why the Sun spins slightly off relative to its planets. Over billions of years, a massive body in an inclined distant orbit could have gradually tilted the entire planetary disk relative to the Sun, or equivalently, tilted the Sun relative to the disk. None of these observations definitively confirms Planet 9, but they're independent lines of evidence that all point in a similar direction. That's what makes the hypothesis scientifically serious rather than speculative. The Vera C. Rubin Observatory, a wide-field survey telescope in Chile, began full science operations in late 2024. Its legacy, survey of space and time, will photograph the entire southern sky repeatedly, to a depth far beyond what any previous survey telescope achieved. If Planet 9 exists and is within roughly 800 to 1,000 astronomical units of the Sun, Rubin has a reasonable chance of detecting it within the next 5 to 10 years. If it's currently at the far end of its orbit, perhaps 1,200 to 1,500 astronomical units away, it may be too faint even for Rubin. There's also an alternative explanation for the orbital clustering that requires no planet at all. In 2019, Anne-Marie Madigan at the University of Colorado and colleagues proposed that the clustering is self-generated, that the collective gravitational pulls of the extreme KBOs on each other, accumulated over billions of years, could produce the observed alignment without any unseen large body. This is called the inclination instability hypothesis, or collective gravity hypothesis. This is where the field genuinely stands. Two mechanically plausible explanations. Current data can't clearly distinguish between them. Better telescopes might. Chapter 9. What other planetary systems tell us? Here is something relevant that often gets left out of Kuiper belt discussions. We've now confirmed the existence of more than 5,700 planets orbiting other stars. The data from the Kepler Space Telescope, which operated from 2009 to 2018, and from the TESS mission still running today, has produced a detailed statistical picture of what planetary systems around Sun-like stars look like. And our solar system is unusual. Specifically, the most common type of planet in the galaxy appears to be what astronomers call a super-Earth, or a mini-Neptune. Bodies with masses between roughly 1 and 10 Earth masses, orbiting their host stars at distances between about 0.1 and 1 astronomical unit. Surveys suggest that 30 to 50% of Sun-like stars host at least one planet in this size range at these distances. Our solar system has nothing in this category. Between Earth at 1 Earth mass and Neptune at 17 Earth masses, between 1 astronomical unit and 30 astronomical units, there's a gap. Nothing. No super-Earth. No mini-Neptune. This could mean two things. Either our solar system formed differently and never produced a planet in this size range, or it did produce such a planet, and that planet was ejected from the inner solar system during the period of dynamical chaos in the early solar system. The second possibility is directly relevant to Planet 9. The Grand TAC model, proposed in 2011 by Kevin Walsh and colleagues at the Southwest Research Institute, suggests that Jupiter initially formed at around 3.5 astronomical units, then migrated inward to about 1.5 astronomical units before Saturn's gravity reversed its inward drift and pulled Jupiter back outward to roughly its current position. This inward migration would have cleared the inner solar system of much of its early material, which could explain why Mars ended up so much smaller than expected. But some versions of the model suggest that a forming super-Earth in the inner solar system might have been ejected during this process. If a body with 5 to 10 Earth masses was thrown outward from the inner solar system during Jupiter's migration, it could plausibly end up in a distant, highly elongated orbit, which is exactly what Planet 9's proposed orbit looks like. This isn't the most favoured origin story for Planet 9 among the researchers actively working on the problem. But it's physically possible, and it connects two otherwise separate puzzles: the super-Earth gap in our solar system and the orbital architecture of the extreme outer solar system. The deeper point is that our solar system's architecture looks like the outcome of unusual dynamical history. The giant planets moved. Material was scattered. The current positions of everything we see are the result of billions of years of gravitational negotiation. The Kuiper belt is where that history is most legible, not because it escaped the chaos, but because the chaos left its fingerprints there most clearly. Chapter 10. What we still don't know. This is the part that often gets skipped. So let's be specific. We don't know the true total population of the Kuiper belt. Current estimates range from roughly 35,000 to 100,000 objects larger than 100 kilometers in diameter. But those numbers come from extrapolating the detected sample, using assumptions about how reflective KBO surfaces are, how their population is distributed across the belt, and how biased our surveys are toward finding objects in particular sky regions. Every one of those assumptions carries real uncertainty. The total number could be meaningfully higher or lower. We don't know whether the Kuiper cliff at 48 astronomical units reflects a genuine absence of material or a current detection limit that future telescopes will push through. The Rubin Observatory should clarify this significantly. If KBOs start appearing in abundance beyond 50 astronomical units as Rubin goes deeper, the Kuiper cliff was largely illusory. If it persists even with Rubin's depth, it's a real dynamical boundary. We don't know whether any Kuiper belt objects harbour subsurface liquid water oceans. Pluto might. Eris might. Eris has a slightly denser composition, suggesting a more rocky interior. And a rocky interior means more radioactive material decaying and producing heat. Makemake and Haumea are harder cases. If any of these objects have liquid water beneath several hundred kilometers of ice, that significantly expands the set of environments where liquid water and potentially life-sustaining chemistry can persist. We don't know detailed surface compositions for the vast majority of KBOs. Spectral data taken from Earth gives general signatures, but is ambiguous in specific details. New Horizons produced real compositional data for Pluto and Arakoth. Everything else is inferred from a distance with relatively coarse instruments. We've sent one spacecraft into the Kuiper belt. 1. Mission concepts for follow-up missions exist. The most studied is Neptune Odyssey, evaluated in NASA's most recent planetary science decadal survey, which ranks missions by scientific priority to guide NASA's budget decisions over a decade. Neptune Odyssey would orbit Neptune and make targeted flybys of selected KBOs, while also studying Triton, Neptune's largest moon, which appears in virtually every model to be a captured Kuiper belt object rather than a native Neptunian satellite. The Decadal survey released in 2023 ranked a mission to the Neptune system as a high priority, but funding authorization has not yet been secured. Getting to Neptune takes a minimum of about 12 years with current propulsion using a Jupiter gravity assist. Getting to a target at 50 astronomical units takes 15 to 20 years. Nuclear-powered spacecraft concepts and solar sail concepts could reduce these times, but none of those technologies are ready for a flagship science mission right now. The consequence of slow transit times is the Kuiper belt missions require extraordinary institutional patience. The scientists who design a mission today will largely not be working in planetary science by the time data arrives. Chapter 11. The Oort cloud shadow. There's a structure beyond even the Kuiper belt that astronomers have never directly observed: the Oort cloud. Jan Oort proposed it in 1950, 1 year before Gerard Kuiper published his Trans-Neptunian disk paper. Oort was trying to explain long-period comets, comets that fall in from enormous distances with orbital periods of thousands to millions of years. Their trajectories, when traced backward, suggested they were coming from a spherical region surrounding the solar system at distances of tens of thousands of astronomical units. The Oort cloud, in current models, extends from roughly 2,000 astronomical units outward to perhaps 100,000 astronomical units, about 1.6 light-years from the Sun. That's nearly halfway to the nearest star system, Alpha Centauri. We have never directly observed any object in the Oort cloud as a resident. Every Oort cloud object we know about is one that has been dislodged by a passing star, by galactic tidal forces from the mass distribution of the Milky Way, or by a chance gravitational encounter with another Oort cloud body, and has fallen inward toward the Sun, becoming a long-period comet. The Oort cloud's existence is inferred entirely from the orbital characteristics of these incoming comets. But the inference is strong, the orbital analysis is robust, and the modelled population is extraordinary. The Oort cloud is thought to contain trillions of cometary nuclei. Estimates of its total mass vary from a fraction of an Earth mass to several Earth masses, with significant uncertainty because we can only sample it from the rare objects that fall inward. The Kuiper belt connects to the Oort cloud through the scattered disk. Objects can migrate between populations over long timescales. Objects originally in the Kuiper belt get scattered outward by Neptune encounters into the scattered disk. From the scattered disk, further gravitational nudges, including tidal forces from the galactic environment, can push perihelia outward into Oort cloud territory. The populations aren't sharply separated. They're more like different zones of a continuous gradient. In 2017, the first confirmed interstellar object ever detected in the solar system arrived. A small, elongated body now designated 1I/Oumuamua. It was moving far too fast, about 26 kilometers per second relative to the Sun at its closest approach, to be gravitationally bound to our solar system. It came from another star system, passed through ours and left. In 2019, a second interstellar visitor was detected, 2I/Borisov. This one was clearly a comet, complete with a coma and tail, and it closely resembled solar system comets in composition. These objects confirmed what most astronomers already expected. The space between stars is populated by material ejected from other planetary systems, including, presumably, material that originated in other Kuiper belts and other Oort clouds. The solar system itself has almost certainly been ejecting comets and KBOs into the interstellar medium for billions of years. The solar system has a fuzzy, porous boundary, not a wall, more like a shoreline where things regularly wash in and out. Chapter 12. What the Kuiper belt actually is. This is the part that's easy to lose sight of when you're tracking individual objects and individual discoveries. The Kuiper belt isn't just a collection of frozen rocks at the edge of the solar system. It's a record. Every object out there, in every unusual orbit, is preserved evidence of a gravitational event that happened billions of years ago. The belt's structure, the resonant populations, the cold classical belt, the scattered disk, the bizarre orbits of extreme trans-Neptunian objects, is a dynamical fossil. It encodes the history of how the outer solar system formed and evolved. When scientists simulate the early solar system, running models of planetary formation and migration forward in time and comparing the results to what we actually observe, they're essentially trying to read that fossil. They're working backward from today's structure to figure out what initial conditions could have produced it. This is harder than it sounds. Small differences in starting conditions produce wildly different outcomes after billions of years of gravitational interaction. The mathematical tools involved are sophisticated. Running a single high-resolution simulation of outer solar system dynamics over billions of years can take weeks on modern supercomputers. But the Kuiper belt gives us something rare: direct observational data about what the early outer solar system was like. The inner solar system, Earth, Mars, Venus, the Moon, has been heavily modified. Volcanism, plate tectonics, impacts, erosion, and billions of years of chemistry have erased or reworked the original surfaces. What you see on Earth has almost nothing to do with what was there 4.5 billion years ago. A cold, classical KBO in a stable orbit at 44 astronomical units hasn't been significantly modified since the early solar system. Its surface chemistry is as close to original protoplanetary disk material as anything we can currently access. In that sense, a 200-kilometer chunk of ice in the cold classical belt is a more direct sample of the raw material of planetary formation than any rock on Earth. What's coming next matters here. The Rubin Observatory will conduct the Legacy Survey of Space and Time, a decade-long survey that will photograph the entire sky visible from Chile repeatedly to depths no previous survey telescope has achieved. Estimates suggest Rubin could increase the number of known KBOs from a few thousand to several 100,000. That's not a modest improvement. That's a qualitative change in the data. With hundreds of thousands of KBOs catalogued, orbital statistics become much more powerful. The reality or illusion of Planet 9's predicted orbital clustering becomes clearer. The true extent of the Kuiper belt beyond 50 astronomical units becomes measurable. Population models become constrained. The current decade of Kuiper belt science will almost certainly produce more information than the previous 3 decades combined. Chapter 13. Why it matters. It's a fair question. Does any of this matter for anything practical? The honest answer is no, not directly, not on a human timescale. The Kuiper belt isn't going to affect anyone's daily life. The odds of a large KBO hitting Earth on any timescale relevant to civilization are negligible. There's no mineral resource in the Kuiper belt that we'll be mining anytime soon, or possibly ever. But the less obvious answer is different. Understanding the architecture of our solar system tells us how common systems like ours are. If the giant planets move dramatically, if the early solar system was genuinely chaotic before settling into its current configuration, then we can ask, how often does this kind of chaos happen? How often does it produce a stable habitable zone? How often does it create the conditions where a rocky planet at the right distance from its star can hold liquid water for billions of years? These are not abstract questions. They're directly tied to the probability of complex life elsewhere in the galaxy. The Kuiper belt also gives us the best available data on the long-term flux of cometary material into the inner solar system. The late heavy bombardment, thought to have occurred between 4.1 and 3.8 billion years ago, may have delivered substantial water to Earth. Water that could, in principle, have allowed life to emerge. Understanding where that water came from the Kuiper belt via the scattered disk, driven inward by Neptune's migration, is part of understanding Earth's habitability. And Pluto's active geology challenges something fundamental. A body 2,377 kilometers across, 5.9 billion kilometers from the Sun, with a surface temperature of minus 233 degrees Celsius, has mountain ranges less than 100 million years old and nitrogen ice that churns in convection cells today. If Pluto can sustain geological activity under those conditions, then the implicit assumption that small cold worlds in distant orbits are inert and irrelevant is wrong. It was wrong for Pluto. It's probably wrong for other places we haven't looked. This shifts the search for interesting chemistry. And interesting chemistry is where biology begins. Conclusion. In August 1992, a dot moved on a computer screen in Hawaii. 2 astronomers had spent 5 years looking for it. Their colleagues thought they were wasting their time. The dot was 160 kilometers across, orbiting 6.2 billion kilometers from the Sun. Since then, thousands of objects catalogued. One spacecraft, 9.5 years in transit, revealing mountains on a world we thought was frozen and dead. A second flyby of the most distant object ever visited, a small double-lobed thing that formed so gently it looks like 2 soap bubbles pressed together, and an orbit signature that doesn't add up. Dozens of objects out beyond 50 astronomical units, all pointing in roughly the same direction, for reasons that might be a hidden planet or might be a statistical trick, and we genuinely don't yet know which. The Kuiper belt is 33 years old as a studied thing. The solar system is 4.6 billion years old. We're reading the first pages of a very long document. Rubin is running. Mission proposals are moving through review. The next generation of astronomers are going to see things in the outer solar system that the people who built the current models didn't know to expect. The answer to what's actually out there is coming. It'll take time. It always does.